Hey there, it's Shannon Math Chick Myers, and today we'll be looking at section 14.7 from the calculus text by Larson and Edwards, and this covers triple integrals and other coordinates. So we'll be able to make triple integrals that are in rectangular coordinates, believe it or not, easier to evaluate using cylindrical coordinates or spherical coordinates. So let's warm it up by just reminding ourselves about cylindrical and spherical coordinates. So if you need to, go ahead and grab your notes to remind yourself. You may not have memorized these things yet. So for number one, we're going to find an equation in cylindrical coordinates for the equation x squared plus y squared minus 3 times z squared equals 0. So if you feel confident, go ahead and pause the movie, warm it on up. Otherwise, you can work it with me. Ready? On your mark, get set, go! I know you can do it. Woohoo! Okay, let's see how you did. One thing to remember is that x squared plus y squared is beautiful r squared. So here, if you look at this part of the equation, we get our r squared. And then we still have our minus 3z squared hanging out, and that's all equal to 0. So typically we would isolate the r squared, and that would give us 3 is equal to 3z squared, and we're good to go. So that one wasn't so bad, right? Awesome. Okay, so number 2, find an equation in spherical coordinates for the equation x squared plus y squared minus 3z squared is equal to 0. So the same problem, right? So let's go ahead and just substitute in for x and y and z what they are in the spherical coordinates, all right? So recall that x is equal to rho times sine phi, and then we have cosine theta, and that's going to be squared. So for our x, we get this here. And then working on our y, so we're adding y squared, so y is equal to rho, and then this time both of them have your sine phi and then this will have times sine theta, and that quantity is also being squared. And then we'll have minus 3 times z, if you recall, is rho times cosine phi. And that's going to be squared. And that's all equal to 0. So here we go. Notice that they all have a rho squared, but what I'm looking at here is that we're going to end up with the first two terms with being able to factor out a rho squared and also a sine squared phi, and then we'd have remaining cosine squared theta plus sine squared theta, and then we will have minus 3 rho squared cosine squared phi, and that's all equal to 0. So now remember that this right here is equal to, beautiful, 1. So now factoring out our rho squared, we will have sine squared phi minus 3 cosine squared phi is equal to 0. So rho squared is 0, which would give us rho is 0, or we would have sine squared, good, of phi would equal to 3 cosine squared of phi. And then, so working with that one, what's going to happen, if I divide both sides by cosine squared of phi, I'll end up with tangent squared of phi is equal to 3. And then square rooting, we would have tangent phi is plus or minus root 3. And where is that going to happen? If you recall, what are the bounds on phi? Beautiful. 0 is less than or equal to phi is less than or equal to pi. And so solving for this equation, phi will equal to pi over 3 for the positive root 3, and then in the second quadrant, good, we would have 2 pi over 3. Groovy? Now, and what you end up having here is an elliptic cone, okay, in 3D. So you would end up having something like this, and your first picture for phi equal to pi over 3, right, is going to end up being so that this one would be phi is pi over 3, and then you'd have phi is 2 pi over 3 is going to come down further, right? So this would be somewhere around here. Oops. All right. And then, and I don't know how fabulous this drawing is. Don't hold me to it too much. But what would happen is you'd have something along these lines. Something like that. So you'd have your elliptic cone going on, and that's something, of course, you could also graph using a 3D grapher. Okay, so here we go. Cylindrical coordinates, recall, x is r cosine theta, y is r sine theta, z is equal to z. So the iterated form of the triple integral in cylindrical form. So if Q is a solid region whose projection R onto the xy plane can be described in polar coordinates, that is, Q is equal to x, y, z, some ordered triple such that x and y is in R, and h1 of x and y, so that the range basically is between h1 at x and y and h2 at x and y inclusive. R itself would be equal to r theta. Now we're in polar coordinates where theta 1 is less than or equal to theta, which is less than or equal to theta 2. And then r is going to be bound by g1 at theta and g2 at theta inclusive. And if f is a continuous function on the solid Q, you can write the triple integral of f over Q as, so this is what we would have, the triple integral, this is over Q, of your function of x, y, and z dv is going to equal to, so we'll have theta 1 to theta 2. The middle one is going to be g1 at theta to g2 at theta. And then this most inside integral will go from h1 at, these are the polar coordinates, which are, don't be too intimidated, r cosine theta is just your x, right? And r sine theta is your y. And then we'd have h2 at r cosine theta, r sine theta. And then we would have our function at r cosine theta, r sine theta, and z. And remember, you've got that extra r when you're going to polar coordinates, and then this would be dz, dr d theta. Cool? All right, so spherical coordinates, if you recall, you've got your angle phi, and it's coming down from z. So here, what would happen is we would have our, so if we take a look here, I'm going to go ahead and kind of sketch out an R. This would be our R, and then that's in the XY plane, okay? And so what's happening is theta is going from our x-axis to R, so that is theta. And then we would have coming up from R, depending on the rotation for phi, you would have, this would be your rho, and then that of course goes parallel to R on our z-axis there, to our z-axis, and then you would have your I should do a different color. This would be phi, this rotation. And then we've got our phi is in between 0 and pi inclusive. Cool, cool? All right, so now let's go ahead and take a look at the iterated form of the triple integral in spherical form. So you would have our region Q, or really a volume Q, and then you'd have f of x, y, and z dv, and that's going to equal to the integral from theta 1 to theta 2, the integral from phi 1 to phi 2, and the integral from rho 1 to rho 2, and then f at rho sine phi cosine theta, that's our x, and then remember that our y is rho, and we have both signs, so sine phi sine theta, and then our z is rho cosine phi. And then that's going to be, we have to have our rho squared sine phi to switch into cylindrical for the iterated integral. And then that's going to be d rho d phi d theta. Actually, sorry, I'm going to move this bit over. There we go. So now let's take a look at some examples. So first of all, let's just practice evaluating the iterated integral once it is in terms of either, this one is in spherical coordinates, and then the example 2 is in cylindrical coordinates. So let's just practice. All right. So here we go. We will end up having. Remember, our very first integral is we are integrating with respect to rho. Okay? And so e is being raised to the negative rho cubed, and so we have the rho squared in place, but what we're going to need is what? Beautiful. We need to have a negative 3 in here in order to integrate. So on the outside of our integral, we'll adapt by a negative 1/3. Okay? And then that will equal to negative 1/3, the integral from 0 to pi halves, the integral from 0 to pi, and then when we integrate this one, we'll end up with beautiful e to the negative rho cubed. And that's going to be evaluated from rho equal to, what was it, 0 to rho equal to 2. And then we'll still have our d theta, d phi. So, just so you can see what came out of there, we've got all of this is equivalent to the negative 1/3 on the outside and then evaluating here. Cool, cool? All right, so this will be negative 1/3 integral from 0 to pi over 2 integral from 0 to pi. And then, let's see, we'll end up with e to the negative 2 cubed, which is e to the negative 8, and then minus e to the negative 0, which is just going to be 1, and then d theta d phi. Cool, cool? Okay, so here we go. Now we will have negative 1/3 times the integral. Now, even though this looks complicated, it's just a constant, right? E to the negative 8 minus 1. So 0 to pi over 2, and then this is just going to be quantity e to the negative 8 minus 1 theta, and then theta is being evaluated from 0 to pi, and then we'll still have a d phi. All right, so next up we will have, and I'll show you again, so this particular part is all of this. So the bound of 0, that lower bound is going to 0 out, right? And then we will have a multiplier of pi. So what's going to happen is we will have, and actually, why don't we write it like this? We've got negative pi over 3, okay? And then we've got e to the negative 8, and then minus 1. And then we've just got our integral from 0 to pi over 2. And if you want, you can write a 1. You don't need to. And that would be 1 d phi. And then what's going to happen? Again, all that's a constant, right? So we'd get negative pi over 3 e to the negative 8 minus 1. And then we'll end up with a phi. And then phi is going from 0 to pi over 2. Again, that lower limit of integration will 0 out. Here is what we found. So we found that this integral here is this right here, right? And we had our constant going along for the ride. So now we'll get a factor of pi over 2, right? So we'll end up with negative pi squared over 6 times e to the negative 8 minus 1. Or if you want to pretty it up, you know, you could say that's positive pi squared over 6 times 1 minus e to the negative 8. Either one works just fine. And there you have it. Okay, so now here we go. This is what we're going to do. We're going to sketch the solid region whose volume is given by the iterated integral and evaluate the iterated integral. So here we go. When we're looking at the very first one, okay, what will happen is we will have for 3 minus r squared, right, we're going to be, and that's being, so what we're looking at is this portion here. So for this portion of the iterated integral, okay, we've got 3 minus r squared. So remember, in polar coordinates, z is equal to z. So what will happen is z is being bound by what? Beautiful. So z is bound between 0 and it's bound between 3 minus r squared. Cool so far? All right. And so looking at those equations, right? If you just looked at equating z to the limits, you'd have z is 0, right? So when z is 0, you're looking at the xy plane. And we have z is 3 minus r squared. But what is r squared? Good. It's x squared plus y squared. So if we think about z is 0, what's going to happen? We would have x squared plus y squared is good, root 3 squared. And so that's a circle with radius root 3, right? And what is root 3 approximately? .73-ish, right? So in the xy plane, what we're going to have is a circle of radius approximately 1.7-ish, right? So let's just say each of these is equal to a half, right? So that would give us, well, will that give us enough? I think so. So this would be 1, 2, 3, 4, and we'd have a -1, 2, -3, -4, and same with the x's, 1, 2, 3, and 4, and then we'd have -1. Nope. One. Okay, and then for the z, we'll do the same. Okay, so here we go. So we're drawing this guy in the purple, right? And so this is what we're going to have. So -1.7-ish. So we'd have, and then z, this is for z is 0, and we'd have a circle with radius 1.7. So 1.7-ish. And so this would be our circle. It's too shaky. All right, something like that. All right, and then we'd have, and then we've got working with the z is 3 minus r squared, right? We would have we need to get our heights, right? So let's do a related color here. So now if I look at, on this one, if let's say x is 0, right, we would have z is equal to 3 minus y squared. Cool so far? And for if y were equal to 0, we would have z would be equal to 3 minus x squared. And this is coming from this here. Both those are. Cool, cool? All right, so now let's take a look at those, those graphs. And what we'll have is, it will turn out to look like, and actually, you know what, let's pause before we draw the rest of it, because it's kind of nice to, match what we've done so far with the iterated integral. Okay, so I'm sure we'll be working more here. So now, working with the purple, we would have, this would be the integral from 0 to 2 pi, and then from 0 to root 3. And now, when we integrate r with respect to z, we're going to get r times z, and z is going from 0 to 3 minus r squared. Cool so far? And then we'll still have a dr d theta hanging out. And so that's going to give us the integral 0 to 2 pi, integral 0 to root 3, and then r times 3 minus r squared, and then at the lower limit it'll zero out. And then we'll have dr d theta. So this purple business here had this result, which is this result. Cool, cool? Okay, so here we go. When we are looking at, so let's go ahead and take a look at, for the, continuing with our graph. So that portion of it, if we take a look, we've got our, when x was 0, z was equal to 3 minus y squared. So you would have a parabola opening downward, starting up at 3 with in the yz plane. So we'd be here, and then if z itself was 0, you for that first one, y would be, so this is when y, the first point I did was when y was 0, z would just be 3. But if z was 0, right, then y would be plus or minus root 3. So you would get these points here. And so this is what it's going to look like. And then similarly for our, if y is 0, you're going to have another point up here. And then you'd have these points here. So you'd have parabola opening downward here. Cool, cool? And so your whole solid is that region. So, I don't know. I think I almost make them look worse sometimes when I do this, but I'll try. Now I guess you could do a little shading. A little darker gray maybe. I don't know if that worked out or not. Okay, so anyway, this is what we have going on so far. So coming up. Now, this one is going to end up being, if I rewrite, I'll have 0 to 2 pi, and then 0 to root 3, and then we'll have 3r minus r cubed, and that's dr d theta. So that's going to give us, so remember that means that r is bound between 0 and root 3, which makes sense, you know, r is that radius. So we will have the integral from 0 to 2 pi, and then we'll have 3r squared over 2 minus r to the 4th over 4, and that's going from r is 0 to r is root 3. And that will be the integral from 0 to 2 pi. The lower limit of integration will again zero out. And so this is going to give us, let's see, root 3 squared is going to be 3. So that will be 9/2 for the first one. And then root 3 to the 4th would be, I believe, 9. So then minus 9/4. We still have our d theta left. And then simplifying that, we have integral from 0 to 2 pi, and that's going to be just 9/4 when we combine those. And then we'll have d theta. So then we will have 9/4 theta, evaluated from theta equals 0 to theta equals 2 pi. The lower limit of integration will zero out, so we will end up with 9 pi over 2. And that's in cubic units. Cool, cool. All right, so there you go. That one was a bit involved. Now here, let's do the whole shebang, right? If we do this whole thing, then what will happen is we're going to convert the integral from rectangular coordinates to both cylindrical and spherical coordinates, and then we're going to use the simplest, we're going to evaluate it using the simplest iterated integral. Okay, so let's see what we have. Let's see what we have going on. So z is bound between I'm using those most inside limits of integration. So z is bound between 0 and the square root of 16 minus x squared minus y squared. Cool so far? So if we were to factor out a negative, we'd have 16 minus x squared plus y squared. And x squared plus y squared is r squared. So this would be root 16 minus r squared. Cool so far? Now, y is bound between 0 and root 4 minus x squared. So y is 0 and y is root 4 minus x squared. Well, this would lead us, that's going to be the, upper half of a circle, so, right? So we'd have, we would have y squared, if we squared both sides, would equal to 4 minus x squared. And so that would give us x squared plus y squared would equal to 2 squared. Cool so far? So now let's take a look at what's going to happen with x, and then we can put some stuff together. So now x is bound between 0 and 2, right? So you're going to have x is 0, x is 2. So that's going to tell us, this combination will tell us that, so 0 less than or x less than or equal to x less than or equal to 2 plus y greater than or equal to 0, those two portions implies quadrant 1, or it tells us quadrant 1, right? And so that means that 0 is less than or equal to theta, which has to be less than or equal to pi over 2. Cool? Awesome. So let's take a look, all right? So now for cylindrical, and you know what? We might need to add a page here to get it into spherical. Yeah, before I write on this, let me copy it, and we will add a page. Paste. Okay. All right, so now let's go ahead and have our and complete the problem. I think we have enough info. So this is going to be equivalent to the integral. So remember, when we're doing spherical, we're going to have dz dr d theta. So we found out that theta goes from 0 to pi over 2. So we know that what? Now, if our radius of our circle is 2, then r has to go from 0 to 2, right? And then z is going to just be z. And so we're going to write it in terms of r. So remember that when we isolated z, we got root 16 minus r squared. And then we have an r from the fact that the square root of x squared plus y squared is r. And then we have another r from the formula for converting from rectangular to spherical. So at the end of the day, we get the integral from 0 to pi over 2, the integral from 0 to 2, and the integral from 0 to the square root of 16 minus r squared of r squared dz dr d theta. So that is the iterated integral in cylindrical coordinates. So let's go ahead and check it out in terms of spherical coordinates, right? So with spherical coordinates, let's see what we will have. Okay, so just as a reminder, these were the cylindrical that we found. All right, so now going from cylindrical coordinates to spherical coordinates, if you recall, if you need to review a little, you can go to what was it, 11.7, I think. And so here, if we've got rho is equal to, so now we're working on our spherical, so we're going cylindrical to spherical. So we have rho is equal to the square root of r squared plus z squared well, we know that z is root 16 minus x squared minus y squared, right? So that's going to mean that we will have the square root of r squared plus, actually, I'm sorry, we're looking at this one here. So r squared plus square root of 16 minus r squared, that whole thing squared. So we would have plus 16 minus r squared, which of course would be the square root of (16), right? Because the r squared will zero out, which is just going to be 4. Cool so far? All right. And then this is nice. Theta is theta, right? Theta is equal to theta. And so the bounds on theta won't change. So that means that 0 is less than or equal to theta is less than or equal to pi over 2. And then we have phi is equal to arc cosine of z over the square root of r squared plus z squared well, that's going to give us that phi is equal to arc cosine of, so we said that z was equal to the square root of 16 minus r squared. That'll be over, now the square root of r squared plus z squared was 4. And we also know that the radius, remember we had found that the radius, our r, was 2, right? And so for r equal to 0, so r equal to 0, we would have phi is equal to arc cosine of 1, right? Because you'd have root 16 divided by 4, which is 4 over 4, which is 1. And that would give us phi is equal to 0. For r equal to 2, phi would be root 16, 2 squared is 4, so minus 4 over 4. So phi would be root 12 over 4. Phi would be 12 is 4 times 3, so we would have 2 root 3 over 4, and phi would be root 3 over 2. Oop, and my bad. This would be the arc cosine of each. My bad. Sine. Arc cosine. I'll just rewrite this one. Equal to arc cosine of the square root of 3 over 2. So at what angle input from 0 to pi, because remember that's the bound on phi, do we get an output of root 3 over 2? That would be pi over 6, right? So phi would be pi over 6. Cool so far? So that means that 0 is less than or equal to phi is less than or equal to pi over 6. Groovy? Remember, for spherical, we have what? D rho, d phi, d theta, right? So theta didn't change. It's going to go from 0 to pi over 2. And phi, we said, is going to go between 0 and pi over 6, right? Yep. And then we would have rho is going to go from 0 to 4. Let's work now on that square root of x squared plus y squared, so we can figure out what that's going to be. See if I have any room. So the square root of x squared plus y squared, I need to get that into spherical. So that would be the square root of rho sine phi cosine theta squared plus rho sine phi sine theta quantity squared, and that's going to equal to the square root of, again, we did this earlier, rho squared sine squared phi or phi can be factored out, and then you'll have a cosine squared theta plus sine squared theta, which is just 1. And so this is going to end up being equal to rho sine phi. Now, we know that phi is between 0 and pi over 6, and we know rho has to be positive. So we will just examine the positive root. All right, plus both x and y are greater than 0. So here we go. This will be rho sine phi. That's from the square root of x squared plus y squared. And then we're going to have from the formula rho squared sine phi, and that's going to be d rho d phi d theta, and that's going to give us the integral from 0 to pi over 2, the integral from 0 to pi over 6, the integral from 0 to 4 of rho cubed sine squared phi, and then d rho d phi d theta. So, I mean, they're both going to be fairly easy to evaluate. Since the limits of integration are all constants on this one, let's go ahead and do this one. So that's going to give us the integral from 0 to pi over 2, 0 to pi over 6. And then integrating, we would have rho to the 4th over 4 times sine squared phi. And that would be from rho going from 0 to 4. And so notice our lower limit is going to be 0. And so that's going to give us the integral from 0 to pi over 2, integral from 0 to pi over 6. Let's see, I think we'll get 64 sine squared phi, or phi. And so now we'll have d phi, d theta. All right, note that we need to use that power reducing formula for the sine squared phi. So we'll have 0 to pi over 2, 0 to pi over 6, and then 64 halves, because I'm doing 1/2 times 1 minus cosine 2 phi in order to integrate. And that's going to be d phi d theta. So I can bring that 64 halves out to be 32. And then I'll have the integral from 0 to pi over 2. And then I'll have, in order to integrate the second part, remember I'll need to have I'll need to balance it by 1/2. So we'll end up with phi for the integral of 1 with respect to phi, and then the integral of cosine 2 phi with respect to phi is going to be sine 2 phi over 2, and that's going from phi equal to 0 to phi equal to pi over 6. So that will give us, note that the lower limit of integration again is going to zero out. So we'll have 32 times the integral from 0 to pi over 2. And then we will have pi over 6 minus sine of 2 times pi over 6 would be sine of pi over 3. Sine of pi over 3 is root 3 over 2. So we'll end up getting root 3 over 4 when all is said and done. And then, oh sorry, we have a d theta left here. All right, so now, here we go. We can treat, well, we'll just go ahead and integrate. We have 32 times pi over 6 minus root 3 over 4. And then theta. And theta will be going from 0 to pi over 2. So the lower limit will zero out. We will have 32 pi times pi over 2. I'll start working to simplify. Common denominator of these two would be 12. So we would have 2 pi minus 3 root 3 all over 12. And so starting to simplify, the 2 is going to divide out some of the 32. And then 4 divides both of these. So we will get 4 pi over 3 times 2 pi minus 3 root 3. Cool, cool? So not so bad, huh? All right. So anyway, that was that problem there. And you know, it wouldn't have been that bad to integrate this one. I mean, I guess we could do it really quick and see what happens. So this would end up being the integral 0 to pi over 2, integral from 0 to 2 of r squared times z, and that's going to go from z equals 0 to z equals the square root of 16 minus r squared. So that might actually be a little grumpy. Yeah, actually, I don't think this is going to be the easier one to integrate, because you're going to end up with an r squared times root 16 minus r squared, and then minus what, 4r squared, which we might need to use trig substitution on. So I'm just going to say dr d theta. I'm going to say spherical, because that's the whole point, right? Spherical was easier. See, next page. All right. So now, last example, use cylindrical coordinates to find the volume of the solid. So here we go. The x squared plus y squared plus z squared equal to 16 is what? Good, it's a sphere with radius of 4. And then z equal to the square root of x squared plus y squared, I think, is going to give us an ellipsoid. So it's gonna look something like okay. So here we go. So we would basically have, you know, in each of our traces, we would have a circle of radius 4, right? So, you know, you'd have on your x, or your xz plane, and then our yz plane would be like this. And then our xy plane I'm sorry, this really is not a very nice picture. But anyway, let's kind of see what it looks like here. Basically, you got this sphere here. And then you're going to have an ellipsoid, right, for the other one. So this guy here, z is x squared plus y squared, is an ellipsoid. It's an ellipsoid. So that would be z, remember, x squared plus y squared. So if we square both sides, we'd have this. So z squared is r squared. And so z is r, and we choose the positive because r is positive. So putting these together, right, that z is r, and then the sphere, right, because we need to figure out where they intersect. What we would have is, we would have z is plus or minus the square root of 16 minus quantity x squared plus y squared, right? So that's working with the sphere, right? And so z would be plus or minus root 16 minus r squared. But what is z? Z is r, right? From the ellipsoid we were looking at. So r would be plus or minus root 16 minus r squared. Well, if I square both sides, I'll have r squared is 16 minus r squared. 2r squared is 16. R squared is equal to 8. And so r, which is positive, is 2 root 2. So our graph is going to look something along the lines of, we'll have our, again, looking at so looking at kind of a combination of information. I mean, if you look at that sphere, if x and y were 0, you'd get z squared is 16, so z would be plus or minus 4. And we have that obviously for our sphere. So you're going to have, something cut out here. So it's going to be, something kind of along these lines. You'll have so our solid that, so they want us to find the solid that's inside the sphere and outside of this part. So we're going to have to subtract out all of this pink right here. Okay, so we will do that. Okay, so let's do it. This is going to be the result of two integrals, right? So here we go. Do you see that the hemisphere, the bottom part, we don't have to worry about, right? And so the volume of a sphere is 4/3 pi r cubed. And so we would have our volume equals half of that is going to be 2/3 pi, and then it's got a radius of 4, so that's going to be cubed. That's the lower hemisphere. Now, what we're going to do, let me move this over. What we're going to do is we've got something that's symmetric in form. So if I just look at the first octant, right, of info here, then I can multiply it by 4 because there's 4 octants on that top half. So we'd have 4 times. It's going to be a sum of integrals, right? So working with the first one, what we're going to do is we're working with the ellipsoid, okay? So with the ellipsoid, we've got this, we'll have a triple integral, and it's going to be going from, remember, it's a dz, dr, d theta. So remember that z is between 0 and r, because z was equal to r. And so from 0 to r. So we're working with z. Z is between 0 and r. Okay, so we basically are, we're constructing this volume with the iterated integral. So this r is our r from the formula of switching over to polar coordinates. Now don't be confused about what we were doing earlier. We're finding the volume of the shape using an iterated integral. So we're not going to be converting z equals root x squared plus y squared and putting that r inside, because we've taken care of it on the limits of integration there. And so this is going to be dz dr d theta. Now theta, well, let's do r. R is going from 0 to 2 root 2, as we found, and that we found that by equating, finding the intersection points of the ellipsoid and the sphere. And then theta is in this first quadrant is just going to go from 0 to pi over 2. Cool so far? So we've got part of it now, all right? Then we'll add to that the next part. So plus, sorry, I'll put it below here, it's still in the brackets, plus the triple integral. Now, this one, again, we'll have a dz dr d theta situation, and we'll have our r dz dr d theta. But now we're going to look at when, we're looking at the fact that z is equal to root 16 minus r squared. It's going to be the positive because we're in the first quadrant. So if we take a look at our sphere, right, and the fact that we have, we're checking this part out. So z is equal to root 16 minus r squared. Well, if r is 0, right, z would be root 16. This is for r equal to 0. Z would be 4, right? For r equal to 2 root 2, right, that would be z equal to, well, 2 root 2 squared was 8, right? So again, you'd have root 8, and you would get 2 root 2. So basically, now you're taking, on this one, you're taking r from to the sphere. So you're basically finding the volume from the 2 root 2, which is the bound we found from the ellipsoid, and you're taking it to r equal to, when r is 0, what's going to happen is that's going to take you to the the sphere itself. Okay, so you're going outside the ellipsoid to the sphere. So add these two together and you're going to get the whole thing if you times it by 4. And then, of course, theta is still 0 to pi over 2. Cool, cool? So the volume would end up being 128 pi over 3 from just that formula, plus 4 times, what are we going to have? Integral 0 to pi over 2, integral 0 to 2 root 2, and then we'll have RZ. Z is going from 0 to R. And then we'll still have dr d theta plus integral 0 to pi over 2, 2 root 2 to 4, and then we're having RZ, and then Z is going from 0 to root 16 minus R squared. Good so far? Okay, and that's the end of that one. So our volume will be 128 pi over 3 plus 4 times. So the lower limit of the first one zeroes out, so we'll end up with integral 0 to pi over 2, integral 0 to 2 root 2 of R squared dr d theta plus integral 0 to pi over 2, integral of 2 root 2 to 4, and then lower limit is going to zero out, and the upper limit is going to be root 16 minus R squared. So we'll have R times root 16 minus R squared, and that's going to be dr d theta. Okay, and probably need to go down again more. So actually I'm going to say see second page below. All right, and so we'll have our volume will be 128 pi over 3 plus 4 times. So when I integrate this guy here, I'm integrating R squared with respect to R. So that's going to give me, so I still have my integral from 0 to pi over 2. I'm going to have R cubed over 3. R is going from 0 to 2 root 2, and I'll still have a d theta. Integrating the next one, we're going to need to balance that out. We need to have a negative 2, right? A negative 2. So if I multiply on the outside by a negative 1/2, I'll balance it, right? So I will have minus 1/2 integral 0 to pi over 2 of the quantity 16 minus R squared to the 3/2 over 3/2, because I had a square root, and that's going from R is 2 root 2 to R is 4, and I still have a d theta left. So the volume will be 128 pi over 3 plus 4 times, okay, so r cubed over 3, I believe, will be 16 root 2 over 3. And then we'll be integrating from 0 to pi over 2 of just 1 d theta, right? And then, let's see, multiplying by the reciprocal, so 1/2 times 2/3, we're going to have minus 1/3 integral 0 to pi over 2, and then when r is 4, we're going to get 0. When r is 2 root 2, we're going to get 8, or 16 minus 8 is 8. So 0 minus it'll end up being 2 root 2 cubed. Doing a little algebra. We still have our d theta. So the volume will be 128 pi over 3 plus 4 times 16 root 2 over 3 theta. From theta is 0 to theta is pi over 2. And then minus minus will be plus, and this one will end up being 16 root 2. So we'll have 16 root 2 over 3 of times theta. From theta is 0 to theta is pi over 2. So let's see, volume is 128 pi over 3 plus 4 times, the lower limit will zero out. So we'll basically be doubling, the result of one of these. So I think we'll get 16 pi you know what, I'm just going to do it out. I'm a little tired. So we'll have 16 root 2 over 3 times pi over 2 plus 16 root 2 over 3 times pi over 2. Our volume will be 128 pi over 3 plus 4 times 8. So that would give us 16 root 3 pi over 2. Over 3. So our volume would be, let's see, we can take out a 64 pi over 3 from each of them, and then we'll be left with a 2 on that first part, and then, oh, sorry, this should have been the root 2, my bad. And let's see, so 64, so then we'd have 2 plus root 2 pi. Oh, not pi, just root 2 cubic units. Crazy, huh? All right, well, that's it for today. I hope you had a wonderful morning, afternoon, or evening whenever you're watching this show. And if you like what I'm doing, please subscribe and tell your friends. Bye.